Hello, and welcome to my presentation on the scaling of the vertical velocity spectrum and variance in the neutral surface layer. My name is Michael Heisel from the University of Sydney. My co-authors on this work are Rahul Deshpande from Melbourne and Gabby Catul from Duke. The topic of this presentation is vertical wind fluctuations in the atmosphere. Here we are considering the simplest case of a neutral atmospheric boundary layer. So we have a uniform temperature profile without any effects from temperature or buoyancy on the turbulence. And in this case, what we expect near the surface is that these vertical wind gusts will be proportional to the shear or friction velocity u star. This also corresponds to the momentum flux at the surface. And we also expect that this transfers to statistics of the vertical velocity, like the variance. We have empirical support for this from stability curves for the vertical velocity variance, given here as sigma w squared. It is found to be between 1.5 and 1.7 times u star squared, the surface momentum flux, under the neutral limit. This is coming from fits by Panofsky in the 1970s and later reported by Garrett in his textbook. In Garrett's textbook, you have this figure showing that in the neutral limit, where z over L is equal to 0, you have a large scatter of data points where the variance is somewhere between 1 and 2.25. So there's a lot of uncertainty, but the average of those is somewhere in this finer range of 1.5 to 1.7. It is also helpful to look at how the variance changes with height above the surface. So here I'm showing a vertical profile throughout the boundary layer all the way up to the full boundary layer depth h, where in the lowest 10% or so of the boundary layer you have your surface layer, which includes the roughness regime, and your inertial sublayer that's outlined here with dashed lines. Within this inertial sublayer, you expect that the variance is going to be approximately constant and have that proportionality between 1.5 and 1.7 times the surface flux. We also have theory to support this result, specifically from Townsend's attached eddy hypothesis. This hypothesis envisions a population of eddies whose size increases as you move away from the surface. This population of eddies results in a constant vertical velocity variance that is proportional to the surface flux. However, it doesn't define exactly what the proportionality constant B is. It also results in a fixed momentum flux that is equal to the surface value throughout the entirety of the inertial sublayer. So you expect that u prime w prime will be equal to minus u star squared throughout the entirety of your surface layer. This is very much in line with the constant flux approximation that's often posed for the atmospheric boundary layer. However, since this theory was introduced in the 70s, it has been known that you need to account for finite Reynolds number corrections because this hypothesis is specifically for the high Reynolds number limit, which you expect to see in the atmosphere. So why are we talking about all of this? The reason is that if you start to actually look at really high fidelity data, here we'll be looking at direct numerical simulations, you start to see trends that are unanswered in the literature and don't exactly go along with the theory that we just discussed. The first example that I'm showing here is from closed channel DNS from Lee and Moser in 2015 that have a variety of Reynolds numbers indicated by the shade of the red color in these vertical profiles shown here. And one of the things that you immediately see is that the peak in the variance is increasing as the Reynolds number is increasing. This is in line with the Reynolds dependence that we just discussed on the previous slide. The more interesting result comes from comparing variance profiles across different flow configurations. Here I've fixed the Reynolds number to 2000 such that we would expect that the profile has the same Reynolds dependence in each case, and all of the remaining differences should be due to differences that are coming from the actual bulk properties of the flow. Here I have introduced a pipe flow from Yao 2023 and a zero pressure gradient or ZPG turbulent boundary layer from Solero et al. In 2013. And you see these distinct differences between the different flow cases that are motivating the questions that I hope to answer throughout the rest of the talk. The first is, why is the variance profile not actually constant? In the channel and pipe case, it is almost linearly decreasing within the inertial sublayer, and in the zero pressure gradient case, it's actually increasing. And then why is the zero pressure gradient case so different in terms of how it's changing with height, and also the fact that it's at a much higher value than the other cases? And then finally, the answers to those questions, what implications do they have for the atmospheric boundary layer? In order to start investigating this, I looked at energy spectra. So this gives you an idea of how the variance is distributed scale by scale within the turbulent spectrum. And I started by looking at the spectrum as a function of the along wind wave number, so along kx. And unfortunately, much like what happens if you're looking at temporal spectrum as a function of time, you kind of lose any distinct trend in the vertical variance spectrum due to the fact that you have this very extensive transition from the largest scales to the inertial subrange, and there are very inconclusive results on the scaling of the spectrum. However, on a whim, I looked at the spectrum along the span-wise or the crosswind wave number ky, and it turns out that this spectrum is much cleaner and that you get a very distinct peak that separates the lowest wave numbers from the inertial subrange scales. And so now what we can do is characterize the spectrum in terms of the energy density of the peak and also the wave number where this peak occurs, and then look at how these properties scale and vary across the different flow cases that we looked at. The primary options that we have for scaling come from wall-attached scaling parameters. These are the ones consistent with the attached eddy hypothesis. So they include the distance from the wall, or the height z, and your surface momentum flux u star squared. And an alternative to this comes from a generalized length scale defined using the local dissipation rate epsilon. This length scale comes from David and Krogstad from about 10 years ago. This generalized length scale does a good job of describing and characterizing the scaling of streamwise or along wind velocity spectra, so it works well in delineating where the inertial subrange starts for u. And it also does well in terms of outperforming the wall-attached scales within the roughness layer of the atmosphere. I'm going to generalize these parameters even further by replacing the surface momentum flux and the surface stresses with local in height stresses and fluxes. So instead of u star, we now have u star z, where u star z includes both the turbulent momentum flux and a viscous component, which is required due to the fact that we're looking at direct numerical simulations which only have modest Reynolds numbers. So this viscous contribution is non-negligible. So what we're going to do now is look at the span-wise wave number spectra normalized with these two scaling options. On the left, we have the wall-attached scaling parameters used to normalize E and the wave number. And on the right, we have the generalized scaling parameters. Looking at a fixed height of 5% of the boundary layer depth across the three different flow configurations, you see that the generalized scaling does a much better job of characterizing and describing what the energy and wave number of the peak is going to be compared to the wall-attached scaling. And so this generalized scaling is going to help to explain some of the differences that we're getting in the variance statistics that come from integrating across all of the scales in the spectrum. Moving to a different height, we're now at about the upper limit of your inertial sublayer, and at this height you still get a better performance from the generalized scales than you do from the wall-attached scales. So there's a better collapse of the cases on the right than on the left. This trend continues as you move even deeper into the boundary layer. So here we're looking at half of the boundary layer thickness. And in this case, the generalized scales are doing an excellent job of characterizing where the peak in the spectrum is occurring and what the amplitude of the peak is. Whereas if you look at the wall attached scaling, it doesn't even get the position of the peak correct, let alone the actual amplitude of the peak. In addition to having a nice collapse of the different curves at different heights, what you can also notice is that this peak and wave number, when normalized using the generalized scales, are pretty much invariant with height across the three examples that I've shown, such that we have this really robust scaling of the spectra with this dissipation-based length scale and with the local and height stress throughout the entire lower half of the boundary layer. So now we've seen that there appears to be this local stress or local flux scaling of the spectrum, and what we need to do to proceed is first clarify what the specific Reynolds number dependence is, because we need to offset the Reynolds number dependence in order to actually evaluate our result. And so in order to determine this Reynolds number dependence, what I'm doing here is dividing the spectrum into a low wave number and a high wave number region based on the peak that we've already observed. And we're going to assume that all of the Reynolds number dependence is coming from the high wave number region. And specifically, when you integrate this high wave number region, you're going to go from the peak position, which is a function of L epsilon, all the way to the dissipative scales, which are a function of the Kolmogorov length eta, such that your integral is going to depend on the separation between L epsilon and eta. This separation can be expressed using a Reynolds number epsilon that I'm defining here simply as the ratio of the lengths. That gives you a very direct representation of the separation of scales that tells you how wide this spectrum is for any given case. What we can do in order to evaluate this integral is to assume that we have a minus 5/3 inertial subrange region that is going to dominate the spectrum. This is particularly true at the high Reynolds number limit. And then we do have to account for shape corrections that are going to occur as the shape of the spectrum changes approaching the actual peak and as it goes through a cutoff in the dissipative region. So we'll account for those shape corrections in a moment, but for now we have a theoretical minus 5/3 component that can be defined using a Kolmogorov constant and the dissipation rate. If you actually work out what this integral is, you actually get that the local stress or the local flux emerges naturally from this integration. The reason for this is because Ky is proportional to L epsilon at the start of your integral. And when you plug in L epsilon for the start of the integral, part of the definition of L epsilon cancels out with the dissipation rate, and the part that is remaining is the local in height stress that we talked about earlier. So this is emerging naturally from the definition that we gave earlier in the presentation for the dissipation-based length scale. You also get a theoretical Reynolds number dependence based solely on the inertial subrange, and then we'll have higher order corrections in a second that we'll add that need to account for the vicinity of the peak and the dissipative region. Here, what I'm doing is showing the integral in the high wave number portion of the spectrum for all of the different flow cases at all of the Reynolds numbers, and I'm plotting it as a function of the local Reynolds number based on the dissipation rate and that separation of length scales. And now I'm showing a fitted line. This fitted line includes a prescribed minus 2/3 relationship that comes from the inertial subrange that we just talked about, and it also has a higher order correction that is fitted to the data that has a -2 exponent, and then also a fitted constant in the front of it that accounts for the fixed amount of energy. And so what we get as a result of this is that we have a variance proportional to the local and height flux that can be multiplied by a proportionality constant. This constant A is not going to be exactly equal to 1.28 because you also need to consider the low wave number region that we haven't shown here. And you also have a correction for finite Reynolds numbers that must be defined using this Reynolds number based on the dissipation rate. So let's evaluate this relationship using the profiles that we already have. So here we're looking at the profiles of all of the direct numerical simulations using the traditional surface scaling of U star squared. And here you can see differences between the different flow cases, specifically for the zero pressure gradient case, and you can also see clear Reynolds number dependencies as well. What happens when we swap out the surface U star squared for the local in height U star Z squared is that you immediately see that a lot of the height variation is taken care of on account of using the local stress. So now you have a lot less height dependence of the variance going all the way from the start of the inertial sublayer up to around 30 or 40% of the boundary layer thickness. However, you still do see some dependence on the Reynolds number because we've not counted for that yet. In this next step, what I'm showing is adding back the energy that is lost from having a finite Reynolds number. So I'm essentially adding back the Reynolds number dependence that is reducing the energy due to the fact that these direct numerical simulations are at modest Reynolds numbers. And after you offset the Reynolds number dependence, you get very good agreement across all of the different cases. And it's pretty much invariant with height all the way from very close to the surface up to about half of the boundary layer thickness. This proportionality constant varies a little bit from case to case. It falls within the range of around 1.45 to 1.65. However, this is a much narrower range than what we started with a couple of slides ago, just using the traditional scaling. This range is centered around approximately 1.55. This 1.55 value matches very nicely with what we see in the atmospheric literature, specifically the lowest limit of the fit that's reported by Garrett in his 1992 textbook. So we are, with this new scaling, U star Z, seeing a good proportionality constant that is matching with what's observed in the atmosphere. And so the key implication for the atmospheric boundary layer isn't so much the Reynolds number dependence, because we're often in a very high Reynolds number case and that isn't affecting our overall variance too much. The more important implication of today's presentation for the atmospheric boundary layer is that instead of having scaling with the surface flux and the surface stress, the vertical variance is scaling with a local in height flux U star Z. This is a really important consideration because something that's often applied in the atmosphere is an approximation of a constant flux within the surface layer. However, this constant flux really only exists for zero pressure gradient conditions. This is a result that comes from the mean momentum balance and how the pressure gradient matches with the stress gradient. And so if you actually look at the flux profiles for all of these different cases, the only one that actually has a relatively constant flux in the vicinity of the surface is our zero pressure gradient case, which is not something that you often have in the atmospheric setting. And indeed, if you actually put a standard profile for a conventionally neutral atmospheric boundary layer, what you get is a stress or a flux that's actually decaying faster than you get even in a channel or a pipe flow. And so it becomes quite important to consider the local stress and flux when you're looking at scaling the vertical velocity variance, because that's going to give you significant improvement over using the surface scaling, particularly as you move farther away from the surface up to the upper limit of the inertial sublayer. That concludes my presentation. Thank you for watching all the way to the end. And next time you are scaling your vertical velocity variance, make sure you are using the local in height flux rather than the surface value.